Okay, so this example is going to employ some concepts that we've just been talking about, specifically resistor reduction and voltage division. So in this case, we are tasked to find current I and voltage V across the 4 ohm resistor. So we can solve this problem using the methods we've talked about in the past that are performing KCL at every node and KVL of each loop. That's totally acceptable. In doing so, we note though that we end up solving for every single current in the circuit and every single voltage across the elements. Sometimes we don't have to do that, as in this case where we only are interested in 2 of those parameters, the current through the 15 volt source and 8 ohm resistor and the voltage across the 4 ohm resistor. So in that case, everything else, if possible, we can reduce it. Okay, you can't always do that, and if you can't see how to do it, then don't go down that path. You always can go back to that brute force method of solving for everything. But these methods may or may not result in a convenient approach. So we do see that attached to this 4 ohm resistor that we care about, we'll actually call those nodes A and B to resemble that in the last example. Nodes A and B are also connected to this resistor network, and we could simplify that into an equivalent resistance Req. So if I pull just that segment out, the equivalent circuit looks like this, where I've got a 2 ohm, 1 and a 2 ohm, and a 6 ohm. So I can reduce this really quickly. So I see right away that the 1 and the 2 are in series with one another, making 3. That's in parallel with the 6, so 3 in parallel with 6, which is 2 ohms. And then that's going to be in series with the 2, so the equivalent resistance between A and B is 4 ohms. So I could go ahead and redraw that entire circuit by putting this segment of the network back into the original circuit, where I have the 8 ohm and the 4 ohm resistor then connected to what I'm calling A and B, connecting to this equivalent resistance, which is 4 ohms. So at this point, if reducing this network in red was a little confusing, I would pause this video and I would go back and I would practice some problems of doing resistor reduction until this is a little bit more clear to you. I went rather quickly through that to get to this point. Okay, so at this point, we can see a couple things. One, I want the voltage across this 4 ohm resistor, but I note that that resistor, is connected in parallel with this equivalent resistance. So we know that elements in parallel have the same potential across it. So this is a case where I can actually combine this resistor with this resistor without affecting the parameter V that I'm interested in. So we note that 4 is in parallel with 4, so that's an equivalent resistance of 2. So I could even redraw this one more time. So we've got an 8 ohm series with a 2 ohm. Voltage is then going to appear across the 2 ohm resistor. And that's my equivalent circuit now. So I can do a few things here. One, I note that all I'm looking for is the voltage across the 2 ohm, and I know that the 2 ohm is in series with an 8, prime case for using voltage division. So I can write right away that the voltage across the 2 ohm is going to be a portion of the 15 volt source. That portion is going to be the resistance of the load that I'm interested in, which is 2 ohms, over the sum of all resistances in the path, which is 8 plus 2. So that works out to be 3 volts. Okay. And for I can do a few things. I know that the total resistance in the path is 10 ohms, so I'm noting that I equals V over R. I know my total voltage is 15 volts and the total resistance in the path is 10 ohms. So that's going to be 1.5 amperes. I could also express I in terms of the individual IVs for the resistors. For example, I could also be found as, I should write that as V sub S, rather that's the 15 volt source, sorry. Could also say that it's V, which is the 3 volt over 2 ohms. And you see that that also works out to be 1.5 amps. So either way we look, we note that I is going to be the same going through the 15 volt source, 8 ohm resistor, or 2 ohm resistor. So you can use each individual resistor to find I, or the sum of the entire path to find I. Either way, you're okay. So here's just another way to solve a problem using some of the tools that we have learned that are element reduction, voltage division. That is to say, don't always look for trying to use those tools to solve a problem. But if you identify certain things about the circuit, such that, like I did in this problem, like I've got a network here where I can reduce it into a single equivalent resistance, go for it. From that, I saw right away that I could use a voltage divider. Go for it. If you don't see those kind of things, don't worry about it. Go back to the methods we know, defining nodes, drawing currents, from the currents, drawing potentials, using KCL, then KVL. That will still work. The more you practice, the more you will start being able to identify uses for the other tools, such as voltage and current division and equivalent resistance. So what I suggest doing is taking this exact same example, trying to rework it using some of the other methods, like the brute force method of using KCL and KVL. Do these kinds of methods for practice until you start being able to identify on your own these other approaches. Thanks.